Hi, everyone. I am Rebecca Wright, Director of Computer Science at Barnard, and it's a pleasure to welcome you here today for a computer science seminar, and a particular pleasure to welcome a former colleague of mine, Amélie Marian, from Rutgers University, who is an associate professor in the computer science department there. She was undergraduate director for many years, and her research interests are in explainable rankings, accountability of decision-making systems, personal digital traces, and data integration. Her recent work on publicly and scholarly explanation of the NYC school admissions lottery process to families in collaboration with elective parent representatives was instrumental in actually making change, increasing transparency and accountability in the New York City high school application system. For those of you like me who had a child who did go to the New York City schools and was part of, I think for us, we did it at the middle school level. I think the increased transparency and accountability is very welcome. So that is good to hear. Amélie received her PhD in computer science from Columbia University across the street here in 2015. And she is also the recipient of a Microsoft Live Labs Award, 3 Google Research Awards, and an NSF Career Award. And she'll be talking to us today about her work pursuing transparency and accountability in decision and data processes.
Thank you for the introduction, Rebecca. So, hi everyone. So a bit about me, in addition to what Rebecca just said. My research background is in data management. My dissertation was on ranking algorithms, and over the years, I've done a lot of work on research in ranking algorithms for various applications, especially applications where data is semi-structured, where you have both content and text in the data, and there's some flexibility in the way users ask their queries. I've also focused on the data integration problems, especially corroborating information from various sources and being able to answer queries where you may have conflicting information coming from various sources. And more recently, I've done a lot of work on personal data and how to integrate and help users make sense of their data and use their own data traces, all the pieces of data that we're creating as part of our daily lives, and being able to search and retrieve information. And I'm going to discuss it at a higher level at the end of this talk. But today I wanted to talk about my more recent focus, which is on accountability and transparency in decision and algorithmic decisions and data processes. And that was stemmed by the fact that in various aspects of my life, school admissions being one of them, I became a participant in algorithmic decision. And after having been the designer of those algorithms, I saw how things don't work as well as expected when algorithms, automated decision process, are applied in the wild. And there are many reasons for that, right? There are design issues where the algorithm, the theoretical algorithms and the guarantees that are defined by the designers of the algorithm actually are slightly changed for practical issues, just because the designers want to add a little flavor here or there, and that has impact on the quality of the outcome and on the guarantees of the algorithm, because algorithms are fickle, right? And a small change may have a huge impact. There are also communication issues in how participants in the algorithms, both the decision makers and the stakeholders, are interacting with the algorithm. Sometimes they don't really understand what's going on, that they make suboptimal decisions in their interactions. And finally, algorithms are implemented as computer programs. And as we all know, there are bugs happen, so errors happen. There are also data issues where the input to those automated decision process may have issues, which ends up, of course, having undesirable outcomes. So over the past few years, I worked with stakeholders and users of different applications of those algorithms to make those processes more transparent and accountable. And why transparent and accountable? For an algorithm to be fair and have fair outcome, people need to trust it and understand it. And you cannot have that without transparency. People won't trust an algorithm if it's not accountable, if the decision makers cannot tell you what exactly. So in this talk, I will start by focusing on an application that affects some of us in New York City, but affects people in the whole wide world. When applying to schools, there are a lot of places where school admissions are handled by a matching algorithm. And as I was a participant in this process when my children were going through it, I realized there were a lot of issues, especially in the way schools were ranking students. And as I said, my background is on ranking. So I looked into how to work with the decision makers, the University Department of Education, the DOE, to make those rankings more explainable and accountable. And then more recently, there were some changes in the process that were not done in a transparent way. And I worked with elected parents representative to push for more transparency in the process and make sure that the process was accountable and any undesirable effects would be solved or at least addressed by the system. Then I'm going to move to another type of automated decisions, one that has even more of an impact, the electoral process. And I'm going to discuss some of the work I've done on ranked choice voting as it is implemented in the United States, where you have absentee ballots and how it changes what happens with ranked choice voting. I'm going to talk about how I integrate all this work in my classes, and then discuss how I worked on making data processes and various data processes, including personal data, accountable and understandable to the users. And we'll give you a brief overview of the digital self project at Rutgers. So the New York school matching. So in New York City, students are matched to school at various levels, kindergarten, middle school, and high school. It's really mostly middle school and high school that creates the whole stressful situation. And the way it is done is that you have two sets of inputs. Students rank the schools they want to attend, but families rank the schools they want their students to attend, based on whatever parameter is important to their families. On the other side, the schools rank the students or prioritize the students based on individual school preferences, school administrators' preferences, or based on system level preferences. So there are priority groups. It could be geography. It could be based on different diversity outcomes that are desirable. In the past, a lot of schools were ranking students based on their academic scores, or they were interviewing students, or they were having, or they still are having auditions. And the algorithm that is used to match students to school is a variation over the Gale-Shapley algorithm, also called the stable marriage algorithm. It was designed 20 years ago by researchers at Columbia, Al-Raf, Padak, and Attila Abdulkadiroglu. And it's well known as the New York High School Matching Algorithm. It's published, you can read it. And yet, it's not that well understood by families. And the Department of Education does a really bad job at explaining how the algorithm works. And they have videos online, for instance, that are wrong. It's not a joke. And so the version that is used for New York City, there are different versions of the algorithm, it's student proposing version. It has some benefits. It is shown to be strategy proof from the student side, which means that you cannot try to game the system. The best decision is always to rank the schools you want to attend in your true order of preference. It also provides the student optimal stable matches. A stable match is the outcome of the stable matching algorithm, which means that there is no pairs of school and students who would be better off eloping with each other, switching with each other. So, that's the theory part of the algorithm. But as I said, as part of design or implementation, there's already issues that pop up. And the way the algorithm is implemented in New York, even from day one, it's not strategy proof. So students can only rank 12 choices. Because they can only rank 12 choices, there is some strategizing in which 12 choice school you add to your list. Because there's a high chance that if you only add schools that are out of your reach because you only add selective academic school, or because you rank schools that for which you don't have geographic priority, you will not get a match. And being unmatched is a really undesirable outcome because the way the system assigns students to school is that puts them in any school. I have a friend whose son was matched to an ASL school for high school. So it's not a good process and it's something you want to avoid. So already we see that the implementation of the algorithm doesn't have the guarantee that the algorithm in the lab have. But so I started looking into this when my oldest was going for the middle school admission. And at the time, I noticed the 12th choice, but for middle school, it doesn't matter as much because you're limited by school in your district. What I really noticed is that the way schools were ranking students, and again, I've done a lot of work on ranking algorithms, didn't make sense to me. And so the problem, and I talked to school principals, and then I talked to contacts at the Department of Education, is that the schools were ranking students. They were asked to rank students, but they had no idea what they were doing. So they would just put a weighted sum function and put weights to various factors or put points to various factors without really understanding what that meant. And that created some weird situation. So here you have two schools ranking functions, those are real ranking functions of schools at the time. School B is a traditional weighted sum ranking function. School A assigns points to various parameters. But it's a very rough bucketizing of students. As it turns out, this is a middle school in District 2 in New York City, which is a high-performing district. As it turns out, in that district, 50% of students at the time had a 4, so between 4 and 4.5 on their test scores, which meant they were assigned the highest number of points. Overall, there were about 40% of students who had the maximum scores for grades, test scores, and behavior. The school could only admit 10% of its applicants. So what made the difference was how many days the student was absent. And that created absolutely madness scenarios where parents in 4th grade, we're talking about 4th graders, would bring their kids to school with a fever in the morning and then pull them at 10 a.m. so that the kid will be marked present. This was before COVID. There are also some legal constraints in how schools can admit students. There is a state law, and here we see that there is a disconnect between the understanding of algorithmic process from the makers and what actually is happening. There's a state law that says that test scores cannot be the primary factor for admission at schools. I don't know what that means. What does that mean to be the primary factor, right? And the way it was translated by school administrators writing their function was, okay, let's not put more than 50% of the points. But I can design a function that only say give 20% of the points to the test scores, but that ends up with the exact same full ranking as ranking students on their test scores. So, and there's a big misunderstanding there. This is due to the fact that ranking function is different from a scoring function. And that's something that is often misunderstood, and it's often misunderstood even by faculty and students. I don't know if you ever asked your students if they wanted to be graded on a curve or on a scale, but the curve is a ranking of students. And well, the answer for my students surprised me. Anyway, so decision makers are often need guidance, and it's not that they were doing maliciously. You know, they were asked to rank students. They took an Excel file and they just ranked the students. So we need to help them find explainable process. So at the time I was working with people at the Department of Education, and I was in a working group on how to improve middle school admissions in the district. And we looked at how to make explainable ranking functions for decision makers so that they understand what impact the weights they put on every parameter matters. And this is work that was published at VLDB with my students, Yehuda Gael. What we based the work on is the observation that it's not just the weight or the number of points in the ranking function that matters, but also the underlying distribution of scores. And that's not a new observation, right? In many applications where you combine information from many sources, multi-criteria decision-making, for instance, there's some manipulation of the data beforehand. But the problem is that this manipulation is often opaque. You normalize every score, and it's not something you can really apply to a school admission function that needs to be transparent to families, right? Telling them your student's grade is now normalized and it's a z-score of 0.3. It's not going to work. I would like that, but it's not going to work. So you need to actually have a scoring function that's transparent to them. And we defined, looked at how each parameter pushes a student in the case selected set, or any object in the selected set, and define a measure of importance that we would then translate into a participation matrix, which roughly gives you the actual weight of each parameter into the decision itself. And to give you an example here with a different application scenario, we looked at a data set from decathlon competitions in the past 20 years or so. So decathlon is a sporting event that has 10 events. And those 10 events, every athlete gets scored on each of them, and the score is then composed as a final score. Each individual event is scored on a different function. The function were designed in the 80s, and they were sort of normalized based on what was the world record at the time. Of course, the world record and the performance of athletes in different events has changed over time. And also the events themselves are not really comparable. You have some speed events, you have some throw events, you have some distance jumping events. And so as time went by, the scoring started putting more weight, more participation on some events. And if we apply our participation matrix on this, we can see that so this is K as a fraction of total items. So you really want to look at this for the winners, but the, what is it, the 110-meter hurdle is actually one of the prime factor in terms of what makes or break who wins a decathlon. Turns out that it's not even there. So 1,500 meters doesn't do anything in differentiating athletes. They're all so close that it doesn't really matter. Okay, we also looked at what was the impact. And as I mentioned, one very important aspect of New York City is what is the bias in the admission functions and how it impacts the diversity of students in the school. And for this, we define a measure of fairness based on statistical parity, called the disparity, that measures how different the selected set is from the distribution as a whole. And we measure that on some studied parameters, right? You can decide to focus on some demographic parameters and not others, or you can decide to focus on everything. It's meaningful for both ranking parameters and non-ranking parameters. Of course, for parameters that are used in the ranking, you're going to expect some disparity. If you're selecting based on your math scores, you're going to have students that are selected at the higher math scores. And so how we measure it is that we compute the centroid of the distribution of the whole population in gray here, and the centroid of the distribution of the selected population, the students that are part of the top K. And this, the disparity is the distance between both, right? And we can compute the disparity one parameter at a time, or the norm of the vector of multiple parameters. And so if you look here on real school data from 7th graders in New York City in 2016, 2017, so we got data from the DOE with real student state scores and grades, using the two scoring function that I presented earlier, school A and school B, with various population, the whole city or the district 2, and various percentage of selected students, we can see on the first 3 columns, those are the ones that are used in the ranking. And yes, there is some disparity. The students that are selected are better at a higher GPA, higher math scores, and higher in ELA scores. However, even though both functions have the same weight for math score and ELA score, you can see that they select more for higher math score. So the math score and the ELA score don't account for the same part of the selection. And now if we want to look what is the disparate impact on the demographic of students, we see that low-income students are really underrepresented. They're 30% less than they should be if they were just a random selection of the population. Girls are overrepresented, which is why the sex here is positive. English language learners are underrepresented, and special education students are underrepresented. And so we have a paper under review at the time right now that explores how we can compensate for that, how we can change our ranking function so that we would not have disparity. And so we presented the disparity compensation algorithm that is focused on the use of bonus points. This is different from what has been used in practice. In practice, most school systems will use reserves or set-asides to guarantee a minimum number of, say, low-income students. But the problem with that is that it only accounts for one dimension of disparity. Or bonus points are composable. So if you have a student who's both low income and English language learner, they will get a boost from both of these dimensions. There's a lot of work on fair ranking that has been proposed recently, but a lot of it is about reprocessing the ranking after the fact, and it's computationally expensive. Our approach is actually very efficient because it's based on the sample. We look at the underlying distribution, either we have the distribution itself, or we have past data, and using the central, there's actually a version of the central limit theorem, the quantile central limit theorem, we can approximate what would be the threshold for K, and therefore identify what would be the best set of bonus points that would minimize the disparity. And here you have an example of such bonus point for 7th grade citywide, where we only select 5% of the students. And by assigning 1 point to low-income students out of 100, so the function is scaled 0 to 100, 11.5 to English language learner, 12 to special ed students, and their 12 points are multiplied by the value that is the economic need factor impact of the school, which is a value between 0 and 1. So it's not a binary set of bonus points, it's a multiplier for that value. We're able to pretty much cancel out any disparity. Of course, there are many applications, and the school matching here is one of them, where the where we don't know K, right? With the school matching algorithm, you don't know how far in the list you're going to go. So we have a version of the algorithm that optimizes for a range of K using logarithmic discounting technique, and you can see that here, optimizing for K between 0 and 50%, we're able to get a huge decrease in disparity. The dashed line is the original disparity. The full back line is the norm of the disparity after bonus points. And same thing, the colors are for the different parameters. So the advantage of this technique is that the bonus points are very easy to understand. People know in advance how many bonus points they're going to get. And it's a transparent approach to minimizing disparity. And the work was planned and proposed as part of a collaboration with the New York City Department of Education. At the time, I was working with the leadership of the District 2 in New York City, and it was part of a working group for a proposal for a grant, the State Integration Plan grant. That was, the plan was to improve diversity in school, and one of the prongs of the plan was to integrate the work I just presented into the ranking function. And the district got the grant, and the state was excited about the project in 2020. 2020 had other plans. So obviously, didn't work out as planned. There were many changes that happened because of COVID, which we all know. In terms of school admissions, for a year or two, there was no grades, there was no test scores, right? So changing the ranking functions would make no sense. So the system had to be revamped and rethought. And what really happened is that, there's only so much you can do with what was there. So at least the first 2 years, and I mean, still today, actually, so for the next 3 years, the formerly screened school just admitted students based on lottery. Sometimes a qualified lottery, but a lottery nevertheless. And that meant that the prime factor for admission was now a randomly generated number. And so the way it's done in the system, the school system, is that every student gets one randomly generated number. This is not a new thing, right? It was always used for tie breaking in the past. It's just that it wasn't the major factor for most admission. And many parents are upset when they learn that, especially if their student has a bad number, because they feel like all the doors have been closed at once. And it is counterintuitive, but there are some research results simulations that show that it actually brings better outcome for everybody. You have more chance of matching to one of your top choices, and about the same chance of being unmatched. But the problem here, talking about transparency and accountability, is like, I was working with elected parent groups at the time. People wanted to know what their lottery number was, at the very least after the fact, but ideally before, so they could take that into account who are building their list. Remember at the beginning of the talk, I mentioned that there's a limit of 12 choices. And so if you have a bad number and you put schools that are popular, you're going to get unmatched. And in fact, the first year or two, people really didn't understand what the lottery was. And you had a very high rate of unmatched students, especially in Manhattan, especially in District 2, because they also removed some priorities. I had over 18% of students unmatched for high school in District 2, and Long Island City, 7%. I mean, maybe it doesn't seem that much, but imagine being a 14-year-old and getting a letter saying, you don't have a school, we'll put you into this school you've never heard of. There's also the fact that if you have a bad lottery number or not a great lottery number, you can manage your child's expectation. We're talking about kids who are 10 or 14, right? So knowing what to expect is important. So we pushed, and the DOE was refusing to tell families what the lottery number was, which blew my mind. You cannot run a lottery in the dark. I mean, there's a reason why the Vietnam draft was done on TV. You need accountability. And so they came up with a lot of excuses. First, they assured us that the number were truly random, whatever that means. And that's partly true, that they would not give information to families as to their relative chances in their preferred school, because their chances depend on the choice of other applicants. That is true, but knowing if you're at the front of the line or the back of the line does tell you something about your chances anyway. And finally, and that's my favorite, they could not share the numbers with families because they consisted of a long string of numbers and letters that the families could not understand. Challenge accepted. So we worked with these parents, the elected parents in an advocacy group, and launched a FOIL campaign. Turns out that the lottery number is used for admissions of students to school, so it's part of their FAIR record, so parents should be able to have it. FOIL is the Freedom of Information Law. It's the New York State version of the Freedom of Information Act. And so parents swamped the FOIL office with requests. They got their lottery numbers. I was one of them. And this is the type of numbers that they got, which is a long string of letters and numbers. Any idea what that is?
UID4?
It's UID4. It's an hexadecimal, right? So now, thanks to me, all parents of high school students in New York City can tell you what an hexadecimal is. It's actually in a UID format, Universal Unique Identifier, and it's a version 4, which you can tell because the third block starts with. Okay. And V4 is a randomly generated number. Now I see them everywhere. When you have a transaction online, you get back an ID and it's a V4, so I can tell you if that would get you into a New York school or not. So with that, only gave us part of the story. How are they processed, right? Are they from left to right? Which one is the most significant character from right to left? And so I ran crowdsourcing experiments. I asked the parents who, and at the time we had the first outcome of that, it was in 21, we had the first outcome of that match, to answer a survey, and comparing students who got into a school and students who didn't get into the school, it was very easy to identify that the numbers were processed in the most logical and simple way, from left to right, 0 to F. And really, parents just need to know the first 2 characters because the system is almost never going to go past that. Right? And so it was very, unlike what the DOE claimed, parents were able to understand it. I wrote several blog posts explaining decoding the New York City school admission lottery. It got over 50,000 hits, so parents were definitely interested into what's going on. And I ran several crowdsourcing surveys over the year. What was interesting is that I wasn't planning to run it last month, but parents and Facebook groups, this year was the first year that the DOE finally relented and gave everybody their lottery number before admissions were due at the beginning. And parents used the results of past survey to generate their list. And many sent me emails saying that it was really helpful for them to manage expectations and tailor their list. And they asked me to run the survey because they wanted to pay it forward for next year. And I also had several YouTube videos explaining the algorithm because, as I said, the YouTube videos on the DOE website are not so great. And so the lessons learned, there's a lot more, and I'm going to give you some highlights, but the lessons learned as part of this experience, I was just accepted as a paper for FACT 2023, where I will present that in June. And some lessons for the survey to see some of the dysfunction. The lack of communication on the process and the lack of transparency is hurting students. Many students wasted their choices on schools they had no chance of getting matched to because their numbers were not good enough, or because their priority did not have seats for those schools. There's a case of, you might know, you have kids in the school with them. It's a case of a very popular K-12 school in New York City where that had thousands of applicants last year. But because they prioritize their continuing students and then they have set aside for low-income students and special ed students, there actually was no seats available for non-prioritized students, right? Which is fine, just tell people and they won't apply. But they didn't tell this, and students had to write 2 or 3 essays for admission to that school. They wrote the essays, and so they wasted time. There was a lot of loss of trust based on that. I mean, it's kind of cruel. But also the schools wasted resources. That school held a dozen open houses, which is a lot of human resources, and teachers graded thousands of essays that didn't matter at all in the process. Right, so we did bring that up to the DOE, and they made it more clear how many seats in each bucket are available. So there are some progress here. They're still not giving the cutoffs. So I recently was awarded a grant to continue this work in this field on transparent and accountable decision systems in collaboration with Ellen Nissenbaum group at Cornell Tech, with legal scholars and policy public policy scholars, and to expand collaboration with current stakeholders such as elected parent representative, elected officials. I've been in talks with the New York State Comptroller's Office, and I've been also visiting the NYU Responsible AI group. And so the work to be performed that we started as part of this grant is really studying the lifestyle of the algorithm, how minor changes, real life changes can impact the outcome and how we can restore trust. And restoring trust is a real problem because there are often errors. In 2019, so before all the lottery thing, there was a lot of errors in the middle school and high school match in New York City. And the reason there was a lot of errors, as we investigated a bit, is that the third-party vendor that was implementing the algorithm had been changed that year. And there's very little information as to how the validation and verification process, and I can take that offline if you have some information. And so how do you account for that? And it's not just New York City. So this is in France. The university system in France, students are assigned to university using a very school proposing version of Gale Shapley. That same year, there was such a big mistake that they had to recall all acceptance and run the match again. Right? And as bad as school admissions are, especially for people who are right in the middle of it, there are many cases where you have errors that are much more impactful. In the UK, there are some problem in the system that was supposed to send screening reminders to women for breast cancer that didn't. And they estimate that hundreds of women may have died because of that. So we're looking at error mitigation in algorithmic process and how to recover from errors and how to be fair to people that were wrong, right? How you maybe reallocate some new resources and who do you prioritize and how do you prioritize them to make sure that the people who were harmed by the first mistake are being, maybe not made whole, but are being prioritized in a better way. And also integrating all of this in education, and I'll say more on this in a few minutes, on how to integrate those real algorithms and how people participate in the algorithmic decisions or in the data decisions with real examples in both a class on data literacy that is an intro class for freshmen and a new class that I recently developed. So I want to move now to a different type of decision process, and I know I'm maybe, because of course school admission is important, but maybe one of the most impactful decision process is how we run elections. And we're in New York, so you may have noticed that some of our elections now have moved to ranked choice voting, so ranked choice voting is a general term for any election system where voters rank their choices, and there is some algorithm that will process those ranking. In the US, the algorithm that is used is single transferable vote, and so I will use RCV or single transferable vote to mean the same thing, but there are different algorithms as well. And so there's been a lot of lobbying group, advocacy group that have pushed towards extending ranked choice voting. So in New York, we use them for local election. There are some states where it's used for statewide elections, but it's gaining traction. And it's seen, and you can see what Fair Vote has a lot of studies on that, to improve representation of women and people of colors in the as voters and as elected, to avoid the spoiler effect. I mean, most of us remember the whole discussion about Nader maybe costing Gore the election in 2000, or maybe not most of us, but it saves money, and that's a big plus for boards of election by avoiding runoff selection. So how does it work? Imagine here that I have a party and I can bring one drink, and I ask people to vote for the drink they want. So Ali would prefer juice, then tea, then soda. Okay, so everybody ranks their three choices. We're looking at the first choice for everybody, and the process in single transferable vote will eliminate the candidate with the least votes until you have one candidate that has over 50% of the votes. So here we have 2 juice, 2 tea, only 1 soda. Soda is eliminated. So the voter for soda, Eva, her vote is transferred to her second choice, juice. Now we have 3 votes for juice. Juice has 3 out of 5. Juice wins. It's a very simple algorithm, but in terms of counting votes, when you have thousands of votes, it does have some issues. It's not as easily parallelizable because it has a blocking operation. You need to finish to count 1 round, decide who's eliminated before you can move to the next one. And in the US, there's a lot of mail-in ballots and absentee ballots, and those are complicating the process because you cannot move forward until all the absentee ballots have been accounted for. Imagine now that you have my 3 absentee ballots. Flocus and Hal come late to the party, right? Their votes are soda, juice, and soda. Now, suddenly, if you look at only the first choices, tea is the first elimination. And because the 2 voters for tea have soda as their second choice, soda wins. So we thought soda was going to be the first eliminated, but as it turns out, soda is the winner. And I don't know if you remember what happened 2 years ago, that summer after the June primary. It takes weeks for absentee ballots to be counted. And in fact, there was a lot of problems with the way this was done. But if you look at the most important election that night, which was the primary for mayor, which was really the election for mayor, on the left, I have election night's results, so all the first choice votes. And for some reason, 1 week after the election, the Board of Election decided to run all the rounds of ranked choice voting without absentee ballots. And it went through the process, and in that case, Eric Adams would have been elected, to be right, against Catherine Garcia. But at the time, there were still 165,000 absentee ballots outstanding. So any elimination could have gone another way. And that's especially true in the second to last round, where Catherine Garcia edged out Maya Wiley by 347 votes. Right? And we didn't know how those, if Catherine Garcia was the one to be eliminated, where her votes would be. Maybe that would push Maya Wiley. And so it doesn't help with the trust in the electoral process if you give some results at some point and then 2 weeks later say, oh, by the way, we have some new ballots that arrived, and it completely changes the outcome. So that following year, I worked with Algorithmic, who at the time was a Rutgers senior, and he did this as an independent project, and we have a paper that he presented last fall at HCOMP on an algorithm to identify who are the possible winners with the known ballots, the one that you have on election night, and with a number of outstanding ballots that are still to be counted. And of course, we won't be able to have the final results because we're missing some ballots, but we can prune out some of the results that are not necessarily possible. And so some result on the 21 primary, what we were able to do is out of 52 races, we were able to identify single winners. So there are some elections for which, and some were pretty obvious, even for from the human eye, but for some of them, just looking at the transfer of ballots, it was obvious that there was only one possible winner. For some other contests, we could tell there were only 2 possible winners, but the second one would need to have such a big amount of absentee ballots that it wouldn't make sense. In this case, it's a council election. the eventual winner, there was only one other runner-up that could mathematically win, but she needed to have 92% of the absentee ballots, where she would be ranked above the other, right? So there's some information there that you could use. And if we look at the mayoral election, it was actually, we couldn't have that much fine-grained information, but what we could tell is that Eric Adams was guaranteed to be the winner, to be in the final two. Andrew Young could be in the final two in one elimination path, but not necessarily, he would never win. And both Maya Wiley and Catherine Graham had path to winning, but the minimum bound absentee ballots or algorithm binds absentee ballots to see if some elimination orders are possible. And this is the differential that is needed. So Catherine Garcia, as part of the absentee ballot, needed 15,000 more than Eric Adams. That it means she needed 15,000 people more than Eric Adams that ranked her higher than him, than he had ranking him higher than her. So it wasn't impossible to have 165,000. However, Maya Wiley needed 66,000 more. So she was very unlikely to be the winner. And so to continue this in this line of work, I'm collaborating with Lirang Jia from RPI on trustworthy and transparent democracy. So Lirang Jia is a computational social scientist, it's their edition, an applied scientist, and we have submitted a proposal to formal method in the field. To continue this work on ranked choice voting, providing algorithmic guarantees. So a lot of work, and I was mentioning that to Canada before the talk, a lot of work that has been done on ranked choice voting is either theoretical work on the properties of the algorithms and how to break ties, but on the practical aspects, ranked choice voting until recently was mostly used in Ireland and Australia. And so the research was done based on the legal processes in those countries. And in Australia, there is apparently some regulation that if you have a small margin of victory, it triggers a recount. Right. As far as I know, there's been no work on ranked choice voting with absentee ballots because that didn't happen until recently in the US. We also are looking at created data sets of cast ballot data and having privacy guarantee. I don't know if you read the news at the time, but when they made the cast ballot data public, there was some issue with privacy and some voters were identified in the data set. So how can we have cast ballot data that is useful for researchers and newscasters that are preserving the privacy of the voters? And one thing that I don't have time to really go into depth in this talk, we're looking at redistricting algorithms. I'm sure you followed the fiasco that was the redistricting of the congressional map in New York last year, where it was so bad that it ended up being completely redrawn by an independent master. So we're looking into providing tools that will build map based on some user-defined constraint and integrating this as a research and teaching tool. And I've already started integrating these and most of the algorithms that I discussed today in my classes. Last fall, I piloted a new class, Algorithms in the Wild, where we're talking about algorithms as they're being implemented in practice. So we cover some theory, but it's mostly the practical impacts of algorithm. And I involve stakeholders as students as stakeholders of the algorithms they're implementing. So for instance, I had them vote for candies that I bring them at Halloween, but more importantly for them, I run a class auction where I auction points on assignments or extensions. I run participatory grading, where we discuss the difference between ranking and scoring and what that means on their grade and how they would want their grade, what they think is a fair grade for the class. And one of the class projects is them redistricting New Jersey. Time.
How many more minutes do you think you need?
5. I'll get a brief overview of the other research. So a brief overview, because of time, of other research work that I've done that is more of my traditional data management research. I've worked with a team of PhD students and colleagues at Rutgers on a digital self project, which is helping users making sense of their own data. We all know that companies are combining learning in their data, creating profiles, but users are not really able to exploit the data that they create. And so we created this model representing all of the data, all the personal digital traces along contextual dimensions, what, where, when, who, what, why, how. And using this as the structured model, we have search algorithms where people can try to find their own data. And in particular, we have your digital self applications where we connect all the pieces of information that are together that as a narrative history. So if you go to a restaurant, the Uber you took to the restaurant, the payment, the chat you had with your friends, all are connected together as episodes, and the restaurant may be part of a trip, right? So to tell a story of a real memory of your autobiographical event. And Valia, who was the main student on this project, has done a lot of development work with this great app. She also has done work on trying to learn new scripts, new episodes with new digital traces, because new apps and new ways of creating data are created all the time with a very interesting game-based approach that is based on the game that's push the button or Among Us type of games where people are trying to hide from a policeman and give alibis based on their personal digital traits. So this whole project, and again, I'm going really fast, is about organizing and summarizing personal data to really have this memory aspect that is created by all those little pieces of data we have. So we can, I can find the restaurant I went in last time I went to a given city, or I can find my expense report faster. Another type of, and I wanted to include that because it's very recent work, but of data processes, there's a lot of information that escaped the data and that's not exploited well. And so Paul is a current undergraduate at Rutgers who's doing an independent study with me. And he came to me after taking the class on algorithm in the wild and was interested in the processes that were around avionics. So Paul is a pilot and he was joining the Air Force. And he felt that, he's flying those small planes and there's data gathered, but nobody does anything with it. It's not clear. And as it turned out, we were a few weeks into brainstorming what we could do about the project, and he had an emergency in flight, some all pressure emergency. And this is his plane on the tarmac at JFK. He had an emergency landing at JFK. But because he had that emergency, he was able to access the data from the flight and to learn what were the processes. As it turns out, on small planes, those are not commercial planes, the data in the flight is kept in an SD card on board the airplane. That is sometimes looked at during maintenance, but maybe not. So, he's now looking at wealth of data and whether there could be flags and triggers that can happen. And really, could we do something about these data processes? Because it's not enough to just gather the data. It should be exploited. Okay, so as a conclusion, algorithmic and data processes are becoming more and more pervasive. And as computer scientists and academics, we have a responsibility to be actively involved in the policy governance and oversight of systems. And for this, we need to collaborate with decision makers. We need to collaborate with legal scholars, legislators, stakeholders, and make sure that we follow the algorithms through their life cycles. It's not enough to have an algorithm that has all this guarantee. We let it loose in the wild and suddenly all the changes completely changes the way it behaves. And for this, we need to expand computer science education. Of course, we need to make sure that computer science students understand the impacts of the systems they design, but also we need to make sure that the future decision makers, the future legislators have some competency in and some literacy in some computational literacy. And I want to finish on the words of Dr. Alondra Nelson, who was recently interviewed, and she worked at the White House, and she recently led the development of the blueprint for an AI Bill of Rights. You might have seen that. And she emphasized that it's time to seize the moment. There's an AI moment right now, and that policymakers should act now to create a future where the AI is at the service of the public good. And I want to add to this, as academics, we should be part of this discussion, and we should make sure that we train the future policy makers and the future system designers so that they are part of this as well. Thank you.
We have some time for questions. People on Zoom, you can be heard in the room if you unmute, so feel free to unmute or raise your hand and unmute and ask questions. That way you can also put questions in the chat and I'll relay them. And of course, people in the room, you know how to ask questions as well.
Could you say more about how the bonus points work? Are bonus points just like another category, like GPA, where you rank them independently, or
You just add them. So
at
a student
the end or the beginning, or
it's just a constant plus as part of the function. So let's say it's 50% GPA, 50% scores, and you have 10 bonus points. The value would be, I don't know, 88, and that would bring you to 98.
I see.
So yes, in some dimensions, you really need a lot of bonus points to remove the disparity.
We have a question in the chat from Joel Saltzman. Can you please elaborate on the ranking of districting plans in New Jersey?
On the ranking of what?
Districting plans in New Jersey. I think you mentioned it as an assignment your students do.
Yes. So I'm not sure on the ranking of districting plans.
Joel, do you want to clarify your question?
Sure, I just assumed that if you're studying districting
We hear
plans
you.
and ranking, that there's something
We did hear.
in the intersection of that would be your focus.
Sorry, we heard you for a second and then we lost you. The intersection of.
Ranking and districting, I would assume that that's what's going on, but maybe you could just elaborate on what that project is that your student is involved in.
So the redistricting was a class project where I had the students create algorithms that, and mostly I gave them basic algorithms. So there are different algorithms that have been presented in terms of how to build a map, a redistricting map, but I wanted them to think about what constraints they would add to the algorithm. So it was a class project. But in terms of the research, what we're looking at is how to build a system. And, even as a class project, I realized it was a bit much for the students. So having a tool where they could, so creating a tool that researchers, students could use where we have rules and constraints and maybe counterfactuals so that several maps would be created that would match some of the constraints that you input to the system.
Okay, thank you.
Just the ranking work. So is the core challenge that normalization doesn't work or that it's not interpretable?
That is not interpretable. Normalization works.
So normalization does solve the problem.
It does solve the problem of normalizing and making, well, you still have to understand what you're doing and, making sure that the decision makers, when they say 50% of grades, that's really what they want because they don't necessarily understand it. But normalization, you can find normalization that will work. But now, if you're in a public policy situation or public good situation, telling people, well, these are your grades and this is the Z-score of your grade, it's not going to be accepted. There's already a lot of distrust of the whole process. For instance, I didn't touch this, but when people saw their lottery numbers, they were convinced that it was so long because things were hidden into it. I'm pretty sure it was so long because whoever worked for the third-party vendor that implements the process was tasked with using a random number, and they Google truly random number, and the off-the-shelf library is the UIDV4. So when I saw that, I was actually pretty relaxed in terms of, I don't think there was any malicious intent there, but you cannot imagine how many parents tried to convince me that they were being discriminated by geographic areas or so on, because by default, if people don't get what they expect or they want, they'll see some malicious intent there.
Two maybe related questions. The first is, do you think we should just force all our policymakers to just write code instead? But that's just the joke. The second question is, with the issues in the Supreme Court around affirmative action, does the model here with bonus points and all of this maybe give some more transparency and offer a way forward that avoids some of these issues?
I knew I was likely to have that question. I'm not sure because I'm not a legal scholar, so I don't know. There are definitely some dimensions that you cannot choose. I think, and that's why New York City uses a lot of reserves for low-income students, because that's considered legal. So it's possible that that could work. I'm not sure how universities actually admit students. I tried to get data from Rutgers, didn't get me anywhere. And I'm sure some universities are even more secretive about what they're doing. Could be, a distinction between public university and private universities. So I don't know the legalities of it. It could be one approach that because it's transparent and people, and it's, if you justify it well, in a way, the whole discussion around personality score was sort of a malice point or bonus point. So you have to be careful with that.
Am I understanding this correctly that that for the ranking system for the schools, that other students' ranking choices also affects their peers' ranking choices? So with that in mind, does the system of bonus points account for, or I guess get away from the fact that there are still certain behaviors outside of the actual behavior of ranking itself? It's like you were talking about, like we hear anecdotally, students that are put in school when they're sick, students who, especially for higher ed admission, students who are put in sports at young age, whatever it might be.
Will they be gaming? Yes, sure. I mean, people are already gaming the system by moving or
Yeah.
declaring a fake address to get the school they want.
Yes.
In terms of, there's some unknown in terms of how deep in their list the school go, although with the crowdsourcing data that I have, I know for some schools how deep in their list. There are some popular school, if you don't have a number that starts with 0 or 1, you're not gonna get it. Some schools go much deeper. And so of course, this bonus points, if you only look at the top 5% and optimize based on that, then that would happen, which is why we have this version that optimizes for a whole range of the ranking. So it doesn't give as good result for one particular value, but because of the unknown, other students ranking the school, it sort of smooths it overall. Does that answer your question?
I think so. Thank you.
All right, seeing no more questions. Let me thank you, Amélie again. Please join me.